You guys have a question or clarification regarding with anything before we start? Nine, all right. How about the others? Before we start, so that we can have a good fresh start, starting right now in finals. So I'm not sure when will be your final exam. So let's see, because I think your final exam will be last week of December or first week of last week of November, or maybe first week of December. Not sure. So let's see, exam days is December. It's first week of December. So I'm not sure if UC will adjust this one into making it to the second week of December, since we've canceled one or two meetings. So not sure. So I hope we can finish our topic today so that we can have another topic next meeting. All right. So last meeting or last week, okay, we've already finished your very first topic in finals, which is the clippers. And then right now, this is like the cousin, okay, or like the brother of the clippers. So have the same idea. It's just that this one has a different concept. Okay, like same idea, but I mean different positionings of a diode. So that's why a little bit the same when it comes to analyzing the circuit itself. So anyway, so for our topic for today, it's chapter 5, clampers. Okay. So first question is, what is a clamper? Okay. So a clamper is basically a circuit wherein it will shift, okay, your signal into a positive side or negative side without changing the shape of signal. Okay. So in clippers, it will change the output because it's clipping, okay, some part of our input. But in clamper, it is not changing. Well, in fact, it is amplifying, okay? It is retaining or amplifying the input signal, okay, without changing the desired level of it or without distorting the signal of it or the shape of the signal, okay. So as you can see right here, we have a very straightforward example. We have a sine wave, okay, wherein it's uh, a sine wave, a positive half cycle and then a negative half cycle. But once it passed a clamper circuit, okay, as you can see right here, this one now is a negative clamper circuit. So negative clamper because it shifts the level, okay, the entire whole level into the negative. So as you can see, this is now the positive half cycle and then the negative half cycle. So basically, the V peak of the positive half cycle now is the zero or the ground in our output. Okay, so vice versa, this one is the negative clamper. So if we have positive clamper, so just put the signal above, okay, the ground level or the zero. Okay, so the positive and negative peaks of the signals can be placed at desired level. So any of those, okay, could be at the up of the ground level or the below the ground level. So with that kind of idea or concept, okay, so we call that one, okay, as a level shifter. Okay, so that is another terminology when it comes to uh, moving a certain signal without distorting or without changing its original form. Okay, so you're shifting it to a certain position without changing the shape of the signal. Okay, so basically, a clumper circuits consists of energy storage elements like capacitors. So this made it possible by not distorting or by not changing the shape of the signal with the use of capacitor. Okay, so this one has a major role in terms of clamper circuit. Okay. So again, once you heard the word clamper, okay, it can change the output or the level of the signal into a desired level. So anywhere on that level. So it could be above the zero or below the zero. Okay, or sometimes it's between. It's getting some part of the ground. So maybe a little bit of positive and then mostly are negative, or a little bit of negative and then mostly are positive. Okay, so that is the very definition of a clamper. Okay, so it can change the level into a desired, or it can change the signal into a desired level. All right, so just a continuation, a clamper circuit can be defined as a circuit that consists of a diode. So it has a diode, it has a resistor, and then an additional of a capacitor. So before we were only using a diode and then a resistor, and right now we're going to use a capacitor in a clamper. Okay, so that's an additional component when it comes to clamper. So in clipper, we only use a diode and then a resistor and then a bias voltage. But in clamper, we're going to use the same, a diode and a resistor, but now there's a capacitor. Okay, wherein it can shift the waveform to a desired DC level without changing the actual appearance of the applied signal. So again, in order for us to maintain that kind of period, without distorting the shape of the level or the waveform, the tau, okay, tau must be greater than half the time period discharging time of the capacitor. Capacitor should be slow. Okay, or in other words, this tau or this period, okay, because this tau is the time of period that it will charge. Okay. Okay. So this is the uh, time period that it will consume to charge our capacitor. So basically, this must be greater, okay, than the discharging time. Okay. So basically, mostly a capacitor can charge 10 times, okay, faster than its discharging time. So, well, some capacitors, or mostly I think 95% capacitors will charge at a rate of 5 times, okay, 5 times faster than its discharging time. So it's not 1:1, okay. So capacitor charges faster than its discharging time. So mostly it's 5 times faster. Okay, so that's how a capacitor works. Wherein R is the resistance of the uh, circuit, and then C is the capacitance of the capacitor. So just multiply it for you to be able to get the time period that it consumed to charge the capacitor. Okay, so we will go to this one later on once we've understand how a clamper circuit works. All right, so the time constant of charge and discharge of the capacitor determines the output of the clamper circuit. Okay, so if we have, let's see, a lesser charging time and then a faster discharging time, then it won't be able to work as a clamper. So it should be, okay, it is a requirement in clamper that the time of charging should be greater or at least equal, okay? At least equal or greater than the discharging time. So that's the only way that our clamper circuit will work as a clamper circuit. So in a clamper circuit, a vertical shift of upward or downward takes place in the output waveform, okay, with respect to the input signal. So yeah, anywhere of the vertical axis. So the load resistor and the capacitor affect the waveform. So the discharging time of the capacitor should be large enough. Okay. So it should charge fast enough, and then it should discharge large enough in our circuit for us, or yeah, for it to work as a clamper circuit. Okay. So we have three types only of clamper. So we have the very two basic, okay. The positive clamper, wherein it will shift the level to the above the positive, okay, or above the uh, ground level. And then we have the negative clamper, wherein it will shift the voltage output or the voltage waveform below the ground level. And then we have the clamper with biasing voltage, wherein this one can shift above the zero level, or it can shift below the zero level, or sometimes it can shift between the zero level and then the positive, or zero level or the negative. So depending on the bias voltage. So later on, you will see all kinds or all possibilities, okay, of bias voltage. So first, let's talk about positive clamper circuit. So again, if you have, or if there's a part that we didn't understand, so feel free to ask, okay? So don't be shy or don't be afraid to ask, okay? So ask right away, okay? Possible. So that we can go over and that topic, and then, we can discuss it as soon as possible. So first, positive clamper circuit. So what is positive clamper circuit? It is a clamping circuit that stores a DC level wherein when a negative peak of the signal is raised above to the zero level, then the signal is said to be positively clamped. Okay. So a passive clamper circuit is one that consists of a diode, a resistor, and a capacitor. So this is our capacitor, this is the diode, and then this is the resistor or the load resistor. And that shifts the output signal to the positive portion of the input signal. So positive clamper, it clamps the signal to the positive side, okay, or above the ground level. So the figure below explains the construction of a positive clamper. Okay, so we will go step by step on how we've got this kind of waveform. So first, how does it work? So initially, okay, so initially, when the input is given, the capacitor is not yet charged and the diode is reverse biased, the output is not considered at this point of time. Okay, so just consider this a circuit. Okay, and then of course we will start at a positive cycle. So positive and then negative. So as you can see, positive is connected to the negative side of the diode. And then negative is connected to the positive. So as a result, this diode will become reverse bias. So what do we say again if it's reverse bias? So let's just say that this diode is an ideal diode. Okay. So what do we do again once we have a reverse bias diode? Anyone? Hello guys, can you still hear me? Hello? All right, so answer my question then. So what do we do again if we have a reverse bias connection to our diode? What will happen? So what will happen to our diode? Okay, I am now being specific. What will happen to that diode if we have a reverse bias? Will it accept a voltage or no? So Brian Doman said that it's open. So if it's open, meaning it will not accept, as you can see right here, it will now, uh, you know, simply make it as open. So our current, okay, our current here will not be able to pass through this node since it's now an open circuit. So as a result, our V sub I, okay, will pass through this capacitor and then will go to the voltage or load resistor. Okay. So as a result, whatever passes through this resistor will be our voltage output. Okay. So as you can see right here, for the positive side, okay, or the passive half cycle, we have this kind of output. So whatever is the V sub I, it is now equal to V sub O. Alright, so our capacitor will not get charged right now since, yeah, all of our voltage input will pass through this voltage resistor or load resistor. Okay, so here's our very first output. Okay, positive only. Alright, so second, during the negative half cycle, at the peak value, the capacitor gets charged with negative on one plate and positive on the other. So the capacitor is now charged to its peak value. Okay, call that one VM or VMC. The diode is forward biased and conducts heavily. Okay, so let's analyze. So we are now in negative half cycle. So negative, positive. Okay, so negative is connected to the negative, and then positive is connected to the positive. So this is our original circuit. So as a result, this will make it forward bias. So if you're going to consider this one as ideal diode, so naturally, this will accept voltage. So as a result, it will now work as a closed circuit or a closed switch. Okay. So during the negative half cycle, we have now a closed loop here. Okay. So same idea with the clipper. If we have a closed loop here, okay, if we have a closed loop here, it will not pass through our, sorry for that one, our dog is noisy. Okay, so as a result, we have a closed loop here, okay, and then it will not be able to pass through our load resistor. So if we don't have a voltage drop or a voltage across this resistor, then we don't have a reading in our V sub O. Okay, so all of our voltages will just loop on this side. Now, this is very important. If we have a loop here, okay, so take note, once we have a loop here in this part or in this capacitor, that's the only time that our capacitor will charge. Okay, so that is why you can see here right now that our capacitor now has a polarity. So how will you know what is the right way for us to say that this is negative and then this one is positive? Okay, so listen carefully. So we have here negative half cycles, negative here and then positive here. So it will charge it negatively, okay? So this capacitor will charge negatively and then we'll leave it positive. So just, I don't know, how will you memorize that one or how will you get familiar, but in charging capacitor, so whatever passes through first the capacitor, it will be the signal of the one. So negative. So negative is connected to the negative. And then positive is connected to the positive. So just memorize it. So negative, negative, positive, positive. So that's how the polarity of our capacitor now. Okay. So it will charge, it will be charged negatively, and then it will leave it, okay? It will leave the capacitor positively. Okay. So yeah. So that's the second step. Okay. So now so let me just write this one so that we can remember. So if you're going to take a look on this one, during the negative half cycle, right, so during the positive first, positive cycle, to go over on this one again. So during the positive half cycle, V sub O is equal to V sub I, okay, because it's completely passing through our load resistor. And then V sub C is 0, okay, or VMC. Okay, let's just name this capacitor, or the voltage of this capacitor, as a maximum voltage capacitor, so VMC. Okay, so 0 because it won't be able to charge, okay, because our V sub I will pass through the RL. So actually it will charge, okay. So in reality, it will charge, but it won't be able to reach the maximum voltage or the peak voltage, okay. So for us to have a peak voltage on this one, we must have a closed circuit in this one. So that's why we have this one, negative half cycle. But for the positive half cycle, it's 0 volts, okay. And then during the negative cycle, so during the negative half cycle, so we have here V sub O is equal to 0. Yeah, because we have a closed loop here. Okay. And then VMC, okay, is now equal to negative positive VI. Because if you're going to read this one, this is now the polarity of our capacitor, or the stored voltage of the capacitor. So positive and the negative. So in my case, whatever passes through, or whatever is the first sign that passes through the load resistor, that is the one that I will consider as its sign. So in our case right here in capacitor, we have a positive sign here that will pass through the voltage output, or the load resistor. So this one is positive voltage input. Okay, so yeah, so this is the V sub O of the positive, and then V sub O of the negative half cycle. All right, so let's move on. So as you can see right here, we have here a 0 volts. 0 volts when it comes to a negative half cycle. And then let's say, let's assume that our VM is -3. So we have a peak-to-peak voltage of +3 and then -3. So -3, -2, and then -1, and then 0. All right. So this is now the crucial part, okay, on why we will get twice of the voltage input. It won't accept voltage. So what is that answer, Mr. Gulaidan? I think you got delayed. I don't know. Not sure. All right. So it will be charged. So as you can see right here, it's, it still doesn't have a voltage output up to this point. Okay. Up to the V peak. Okay. Up to the part that it reached the V peak, the -3 volts. So it will be charged. Our capacitor will be charged up to the maximum voltage of the negative side, or the V peak of the negative half cycle. So as you can see right here, it stops right here during the -3 volts. Okay, so again, this is the crucial part when it comes to capacitor. Once it detects a power loss, okay, let's say VC, V, yeah, VCM is lesser than, yeah, VCM, VMC, not VCM. If VMC, okay, or if the peak voltage of the capacitor is less than the voltage input, okay, then that's the only time that it will release, okay, or it will discharge rather. So let's change the terminology of this one. That's the time that it will discharge its voltage. Okay, so at this point during the -2, okay, -1, and then 0. So as you can see, our voltage input now is less than, okay, the VMC, okay, wherein we have -2, -1, and then 0. And that's the time that it will discharge its stored voltage. Okay, so as a result, we will have, where's that one? We will have up to this part only. Okay, we will have positive 3 volts. Okay, and then during the next positive half cycle, okay, so this is the negative, okay, negative half cycle, wherein we have -2, -1, and then 0. So this is not the discharge voltage of our capacitor. So during the next positive half cycle, the capacitor is charged to positive Vm, okay, while the diode gets reverse bias and gets open circuited. The output of the circuit at this moment will be like this. Okay, so we have a VMC here of 3 volts, or a peak voltage of 3 volts in our capacitor, and then uh, a positive 3 volts also, because we have a peak to peak of 3 volts. So as a result, we have 3 volts here and then another 3 volts here. All right, and then as you can see, we have positive connected to the, where's that one? Here, connected to the negative, and then negative connected to positive. So as a result, this circuit will become open circuit. So thus will not accept voltage across here. So all of our voltages will pass through RL, or the load resistor. So as you can see, if you're going to apply KVL, okay, we have here positive 3 to positive 3 will be added, so 6 volts. And then we'll pass through negative V sub O. So just transpose that one. So V sub O now is equal to 6 volts. Or we have this formula. VO is equal to V sub I plus the peak voltage of the capacitor, or VMC. Okay. So as a result, so again, let's go back here. We have here the discharge portion up to this point. And then we have here the positive voltage during the positive half cycle, which is now another 3 volts. Okay, and then going down here. So that is why we have here 6 volts, and then, yeah, and then completely 0 in our negative side. So hence, the signal is positively clamped as shown in the above figure. So the output signal changes according to the changes in the input, but shifts the level according to the charge on the capacitor as it adds the input voltage. So I hope you guys got the idea, okay? Wherein positively clamp, just, shift it to the above, or yeah, above the ground level, or above the 0. Okay, so we still have a peak to peak of 3 volts. So this is the 3 volts, and then another 3 volts here. So as a result, we have here positive 6 volts. All right. So we have here a summary wherein, if you're going to analyze it, just like what we did before, okay, using the notepad. So during the negative, so we will, so here's the, again, another important part on where will you start. Is it during the negative or is it during the positive? So when it comes to clumper, okay, you have to charge the capacitor first. So for you to be able to charge the capacitor, so you must have a closed circuit, okay, on this spot. You must have a forward bias, or you must have a loop of voltage for you to be able to charge this capacitor to the maximum, okay, or the VMC. So if you're going to take a look at this one, so we have a negative side and a positive side. So basically, you must have a negative sign here and then a positive sign here. So we can only have that if we are in negative half cycle. Okay, so that is why we will start at negative half cycle, because as you can see right here, if we will start at positive, then it will do nothing. We will still get the 3 volts. So our clamper will only work if this capacitor is now fully charged. All right. So I think we now only have 30 seconds. So we will continue the rest on the part 2. All right. So for now, goodbye, and then see you after 5 to 7 minutes.